In this video, I'm going to cover the spectral modeling capabilities of PeakLab. This is a major addition to the PeakLab software technology. Although this was designed to model spectroscopy data to chromatography or other laboratory reference values, the predictive modeling capabilities are general, and they represent a new state-of-the-art for multivariate linear modeling. In every instance where this new predictive modeling was evaluated, it outperformed PLS, partial least squares, PCR, principal component regression, as well as the best forward, backward, stepwise models that could be generated with the human interactive modeling by an experienced statistician. The new predictive modeling is found in PeakLab's model menu. It's a dedicated app within an app that will do the predictive modeling for you. In PeakLab, we generate direct spectral models. These are much more immune to spectral components with inverse correlations. Secondary components are dangerous in the predictive sciences. Those relationships may vanish or they may not be present at all in the new samples that will be used for the predictions. For powder spectra, direct spectral models are much less sensitive to hydrophobic species and moisture effects. Direct spectral fits are also much better at not fitting the noise and being adversely impacted by random chance correlations. The direct predictive models not only offer more effective and robust predictions, they are also far simpler, much easier to understand than the indirect factor or principal component modeling that's used in statistical and unscrambling software for this type of spectral modeling. Now, the predictive modeling software is designed to work smoothly and to integrate with PeakLab's main peak fitting functionality. We will begin by looking at this set of 25 liquid UV vis spectra of curcuminoids, each of which is taken from integrating the 3D diode array data of the chromatography across the runtime of the separations. PeakLab was used to perform this integration of the chromatographic 3D DAD UV vis data. This option is in the File menu. In the Import Datasets, Import Spectroscopy from 3D Data Matrix option here. The option uses a standard ASCII CSV matrix format, the type that's generated by an Agilent export. In this exploratory UV vis spectral modeling, the solvent solution for the spectroscopy is the actual mobile phase of the chromatography. It's a very fast, very efficient way to see if the UV vis liquid spectra can be readily used to estimate chromatographic or other laboratory reference values. If you use the feature Map Experimental Process Variables for all data sets, you can add up to 4 process variables to the PeakLab data file for each of the spectra. In this example, we have put the chromatography values of the 3 principal curcuminoids and the total into the data file. If you store the process variables in the PeakLab spectral data files, the program can build your data matrix for the modeling for you. Here in the Model menu, we'll select the Build Data Matrix from the spectral data files. In this particular case, I'm going to select all of the different data files that you see here. We generated 466 spectral data sets in this option. We have a matrix now that's ready to go. We'll import the data. 466 rows, 617 columns of data. At present, we will not fit this data. We will instead look at the Excel. We'll pull up Excel and look at what the file looks like that we just generated. If you see here, there are 2 identifier columns. The second one is automatically generated from these process variables. We will use this particular ID in the next step to help identify outliers and to see if we can detect some trends in the data before we begin the modeling. In the data file, you will notice that the 4 process variables are in the initial columns after the identifiers, and after that you see the spectra at the individual UV vis wavelengths. We now select the Graph Data Matrix option to visualize the imported data that will be modeled. We're going to set a starting wavelength of 300, and we're going to specify a final wavelength of 500. This covers the upper portion of the UV wavelength band and the lower or blue portion of the visible wavelength band. This is where the curcuminoid compounds have their primary absorbances. We will begin by using the unit area normalization to see if there are any apparent outliers or failures in the spectral procedure. This is also very useful for seeing which data sets represent a bracketing within the model problem and any region of the data within that bracketing which is not represented by a spectrum in the data matrix. Here the data are plotted without lines to make it easy to see all of the data when there are hundreds or perhaps thousands of spectra in the data matrix. The Use Mouse option will add the identifier information to the title and highlight the spectra that is currently below the mouse. You see here we're looking at 3 replicates of this particular sample, which very much stands apart and does represent what we call the bracketing in a multivariate modeling problem. And you can see as we look at this zone right here, we have no data actually represented in these portions of the overall unit area normalized spectra. When you see something like this, it's often of value to just do a blend of that particular material and this to produce some spectra that will cover the bracketed range entirely. As we move through the spectra, we see certain spectra that are much noisier. We see some that are much smoother. We also see, if we look here, we see spectra that are showing a fluorescent spike in the green, about 480 or so. To see any given spectra, just place the cursor on one of the points in the data. We're now going to set the normalization to none to see if we can identify a wavelength or set of wavelengths that generally track the overall curcuminoids that we wish to model. Now this is very important, for there may be one or more UV or visible wavelengths that have a simple and direct correlation with the target analytic variable. This is an example of a modeling problem that is elementary for liquid UV vis spectra and a true unscramble nightmare for doing powder NIR spectra. Now if I use the automatically generated IDs in the data file, I can do something like search for. Here I'm going to put in the total variable, PCT total. And if I put a value 1 dot after this, it will search the strings in the data file to find all of the values, all of the spectra that correspond to a chromatographic value of 1 to 2% total curcuminoids. If this is very useful now, because we're going to go ahead and just change that to a 2. So we'll look at everything between 2 and 3. We're going to now move it to look at everything between 3 and 4. Look at everything between 4 and 5. And here you do see the divergence of those bracketed samples. That these exist because the ratios of the 3 components are drastically different in these particular samples here. So far we see a case where we're tracking very well, and the tracking appears to be out more toward the right side of the overall spectral feature. But this will continue as we go through here. We see what looks to be a lovely modeling problem because it looks like one or just a few spectral values will be giving us the trends that we need to do the effective modeling. I want to show you one more thing. We're up to 9 to 10% total curcuminoids now from the 1%, and you can see we are at a very almost at the maxima here. If I go do just one more, and I look for those with a value higher than 12, we have something that looks like an extreme outlier here. Now, these are triplicates, so there are the replicates here. You should see at least 3 samples whenever we put a value in that's going to fall within a given band. And we have one that just looks like it's out in the middle of nowhere. The next 2 that are a part of that same sample, this S230 that you see here, they are up at the maximum where you would expect them. This other one, this replicate 3, it looks like there's a serious problem with that particular data set. So this is a nice way to go through and determine any suspect data sets before you begin. We will look at one more item before we model this data. This is an average of all of the UV spectra. Here are all 440 plus spectra. They've been averaged, and we're going to fit this to an equal width set of Gaussians. In this case, I'm just going to select that particular optimal fit. For this type of fit, using wavelengths instead of wave numbers is sufficient. It requires some effort, but the best F statistic that you achieve in this type of peak fitting will occur with a certain count of Gaussians, and the SD width of those Gaussians will furnish a lovely estimate of the resolution of the spectroscopy. Here we have 10 peaks in this overall average. One of these is clearly at the end of the spectra. If we look at the data here, you can see by sharing this with the A2 value of the Gaussians, we have 12.7 nanometers as the standard deviation of the fitted Gaussians. Now, when you do this type of analysis, you may not see the actual absorbances of the materials in the specific solvent if there are multiple components and overlapping absorbances, but you will see the wavelengths that can be seen by the modeling. It's a meaningful picture of the wavelengths the spectral modeling will be able to find. If we are looking for a peak in the 425 to 450 band, as we are in this case, the largest peak is at 448, and the smaller one is at 433. We saw where the changes in the ratios of the components made it much more difficult to use a single wavelength out toward the in the UV and the lower visible band. Now, our rule of thumb is to set the X wavelength spacing when you do your modeling to about 1/2 of the Gaussian standard deviation when you do this type of multiple Gaussian fit, and you optimize to get the highest F statistic with the different potential counts of Gaussians. In this particular case, half would be about 6 nanometers. Any spacing appreciably narrower than that will be wasted. It will seriously inflate the full permutation fitting times, and in the extreme it can result in the fitting of noise. For our purposes here, we'll choose 5 nanometers since this will give us a nice set of wavelengths for the modeling. We now have enough information to begin the spectral fitting. We will fit the spectral data as sampled without any form of normalization. The model menus Fit Full Permutation GLM Models opens a simple dialog that controls the spectral modeling. By default, the X prediction filters will pare down the number of available X predictors of wavelengths as the count of predictors in the model increases up to 8. That's the maximum that's allowed in the full permutation modeling. Here you see that with 8 predictors, the algorithm ensures at least 30% of the wavelengths are fitted. The omitted wavelengths will be those that did not appear in any of the safe fits from the smaller predictor counts, or wavelengths that rarely appeared and which did so only in weaker fits. The predictor filters are useful for fits that process a large band of wavelengths, or where the resolution is especially high, as in FTIR and FTNIR instruments. The X wavelength range and the X wavelength spacing. These are the critical items in terms of the modeling time. We'll begin by selecting the variable we wish to fit, and we will select a UV wavelength a little bit beyond the really busy band, and we will specify the upper end of the visible at 480. We'll avoid that small bit of fluorescence that we saw, and we will set the X column spacing at 5. If we do that, we see here that we will do about 93,000 fits, and it'll take about 4 seconds. In this case, we can look at what would happen if we were to remove these filters and fit every possible permutation, something we can do because we've got a 5 nanometer column spacing, and we're covering a fairly narrow range of wavelengths. So if I change this to all, you'll see we fit about 19.5 million permutations, and it's going to take about 14 seconds. The cost for fitting every possible permutation through the 8 predictors is quite small. On the other hand, if we were to set the X spacing to 1 nanometer, we will now be fitting 10 trillion models, and it's going to require about 67 days. And if we actually did this, the end result would be useless. Although we could fit a 1 nanometer spacing using the default filters, and we'd be able to accomplish this in about 12 minutes, there would be no point. The resolution in the spectroscopy does not support a 1 nanometer spacing, nor will the signal to noise in these data. We don't want to fit any systematic noise in the data, only the deterministic or spectral signal data. Now, this issue isn't specific to the PeakLab algorithm. It's also everywhere a problem with forward, backward, stepwise multivariate regression when you're in statistical modeling. In fitting noise, you often see a large positive coefficient at a given wavelength and a large negative one at the adjacent wavelength. The defaults here have been set to give you a very good predictive models using the leave one out prediction errors, and the higher count smart stepwise and the sparse PLS models are also present by default. These allow models in this case to go up to 12 predictors, and these smart PLS models assemble many individual models into a composite that will allow the model to contain up to 15 predictors. The defaults evaluate 1,000 model fits for each of the predictor counts, and we will keep the best 100 using, in this case, the predicted R-squared metric. As you'll note, we have many different metrics you can use to sort the individual goodness of predictions. In general, you will not need to change the defaults. They were designed to get you a very good predictive model. If you use this modeling extensively, you will probably become familiar with the random sampling errors to test for not fully bracketing the modeling problem, the prediction sorting, where you can use more robust metrics, and some of the other options. I will point out 2 of these. The refit to X column spacing equal 1 option adds a final step that searches the omitted wavelengths as a consequence of the spacing to refine the predictions. This is quite fast. It shifts a given predictor up and down in wavelength using the wavelengths that were not included in the spacing. You get the benefit of the higher density of predictors without the issue of fitting noise at adjacent wavelengths. The limit fits to n principal components performs an eigendecomposition in the computation of the fit coefficients. If you know, for example, that your spectral data is effectively noise from the 7th eigenmode or singular value onward, you can set the fitting to process the parameters for 6 principal components in the matrix computations. This can help with minimizing overfitting, and it further defends against the fitting of noise. There is also an option in the model menu to generate principal component data matrices if you wish to fit these separately. We click OK to begin the spectral modeling. As you see, we are consistently getting an R-squared or prediction of about 0.94 irrespective of the predictor count. The upper progress bars are for the full permutation fits. The lower progress bars are for the smart stepwise fits. Now these smart stepwise fits begin with the best of the saved full permutation fits and add additionally statistically significant predictors using a multiple tier search routine. It may perform thousands of exploratory fits in generating just a single final model from an especially strong set of initial predictors. We will first save the full fit information. This is useful for importing a previous fit without having to refit the data. In the upper plot, the X data are the known reference values. Here, the total percent of the principal curcuminoids from the chromatography. And the Y values, these are the percents predicted from the current selected model. We're currently sorting by the predicted R-squared. We're not currently filtering the list. As such, the best model is a sparse PLS model with 14 wavelengths that was built from 45 separate 5-parameter models. If we look at just the performance, the prediction performance in the plot, we see this one massive outlier. It's not a surprise. It's that S230 replica 3 spectra we found visually prior to fitting. This outlier is significantly degrading the R-squared goodness of prediction metric. It's way beyond 3 standard errors. It's why it is colored red. We also see one yellow colored spectral data set. This value is outside 2 standard errors but not beyond 3. This yellow point is also outside a 95% default linear Y versus X prediction interval. This is the blue band you see around the prediction curve. We will next have PeakLab automatically remove the outliers. We select the data option. As you will note, every outlier detection method is currently selected. The first 5 methods use an outside of 3 standard error bound, and the prediction intervals use a 99% confidence interval. If you look at the title bar, you will see that these criterion find 5 flagged outliers. We have 465 total, so only 5 of the 465 are being flagged as potential outliers for this highest predicted R-squared model. We will save the data with the outliers removed, and we will refit. We'll go back out. We will import the revised data with the outliers removed, 460 run rows, 460 spectra. We will refit, and you can see a massive difference now. We are getting 0.992 to 0.993 R-squared values from the fitting. Again, we see only a small benefit from the additional parameters. Now we are looking at the data with the outliers removed. We're going to begin with the fit performance option. This is used to determine the optimum count of predictors. Direct spectral modeling is not an exact science, and we thus show 8 different metrics that can be used to optimize the predictor count. Apart from the last 2 plots, the white curves contain the design or the calibration fit metrics, these which will always be better than the prediction metrics. We will first remove the references and look at only the prediction statistics. And again, these will always be weaker than the design fit statistics. We'll also average the 3 best models for each of the predictor counts. Not surprisingly, the R-squared is at its highest with the 15 predictor sparse PLS models. The standard error is at its lowest with 5 predictors. The F-statistic inverse at its lowest with 1. The Akaike information criterion is best at 5. The Bayesian information criterion is best at 3. The minimum description length best at 2. And as far as the median and the average errors go, you see very high parameter counts as its optimum. Now, often these different metrics will show a good agreement, especially with very difficult to model spectra. Here, because the fit is so effective with just a single predictor, there's a much wider variation. The F statistic is conservative, suggesting 1 predictor. The corrected Akaike is a bit liberal in suggesting 5. The BIC and the MDL at 3 and 2 are midway. We often use the BIC or MDL in our modeling. The MDL will be a little more conservative since it incorporates the F statistic. With your own experience, you should be able to look at these different metrics and select an optimal parameter count. Here, from our judgment, we would choose 3 predictors. It's the optimal BIC, and the 3 in the MDL is almost identical to its optimum at 2. In the model list, we will use the filter menu to display just the 3 predictor models. In the sort menu, we'll select predicted average error as the sort option for the different models. The best model consists of 2 UV wavelengths and 1 visible wavelength. And not surprisingly, the visible wavelength 445 is the wavelength we saw in the multiple Gaussian peak fit modeling we did prior to the spectral modeling. The prediction average is 0.121% of the total curcuminoids. If we look at this model closely, these are the residuals on the top. We'll hide those and look at just the known chromatography data versus the spectroscopy data. You can see there's still a couple of points that are suspect. They appear singularly, meaning that the replicates did not match up. But overall, it looks like a pretty stable model. It looks like a model you'd be fairly happy with in terms of the performance. Now, there are a couple of other items we can look at here, one of which is we get a beautiful map of the wavelengths when you do this type of modeling. This is a map of the wavelength significance in the best retained 3 predictor models. If we look closely, we see the two UV wavelengths have relatively small overall significance in the retained 3 predictor models. It's good, but there are others that are not represented as well. There's an option in the model list menu to sort by X predictor compliance. When we do this, we see the second model in that list consists of 3 visible wavelengths, which might be precisely what you're looking for in this type of model. It has a 0.123% average error in terms of the percent total curcuminoids being measured, and that's almost identical to the model that contained the UV wavelengths. If we filter by only stepwise and sparse PLS fits, and we sort by predicted average error, we can search the PLS models, sparse PLS models that have 3 predictors that consist only of visible wavelengths. This is one here, here's another, here's a third, here's a fourth, here's a fifth, and here's the best of 6. This particular model has 10 wavelengths built from 31 different 3 predictor models. Its error is a little under 0.122 compatible with the others. Here you see many of the wavelengths we saw in that multiple Gaussians fit that we did prior to the spectral modeling, particularly the 435 and the 445 are present here. If we click on the numeric option, we will see the median and the average errors as well as 5 different quintile errors. The different background colors of the plot represent the 5 quintiles in the data. As you go to the larger values, you see that the errors increase as you increase in the quintiles, although it has a dip where at a certain value you're at a minimum. The numeric summary can also contain a full precision export of the selected model. Here you see we have C++ and Visual Basic export options in the numeric summary. For the C++, we'll show 2 formats. The first, where the arguments are spectra specific, where you're only passing the arguments for the individual values that are in the model. This is code for passing in the entire spectra, where the individual wavelengths are parsed and processed separately. In the tutorials for PeakLab, there's a direct spectral modeling of powder FTNIR spectra. This is a far more challenging modeling problem for PeakLab. It's a far more challenging modeling problem for PLS and PCR as well. In the PeakLab documentation, we also show that the direct spectral fits produce more accurate and far simpler predictions. In PLS and PCR, there's a positive or negative contribution from every wavelength made available to the modeling. PLS and PCR models will have a separate parameter for every wavelength in the modeling, meaning there will be some influence at every wavelength, although for certain wavelengths this may be small. Some of those wavelengths will apply to spectral components that have nothing directly to do with the component or components being modeled. They may be inversely related, perhaps a hydrophobicity, hydrophilicity, or moisture effect, or these wavelengths may be in the model simply from random chance and correlations. Direct spectral models have far fewer parameters, and most wavelengths will have no influence at all on the overall prediction. Only the most statistically significant wavelengths are used.